All right, this is 14.2 wave properties. Today we're going to talk about the difference between transverse and longitudinal waves, and we'll calculate wavelength, velocity, and frequency of a wave. With these waves, we're talking only about mechanical waves. We're not talking about electromagnetic waves. We're not talking about like electricity or anything. We're just going to stick with mechanical waves. And mechanical waves are things that you can physically touch. There's three different types of waves. There's the transverse wave, the longitudinal wave, and the surface wave. So the transverse wave is the wave that you think of when you think of a wave. Right? Those things that have been haunting you in math with sine and cosine type waves. The way that you draw them out, that's what a transverse wave would look like. And I can do a very sad example here with my slinky. Here is a transverse wave. And if you go faster, then you get more little waves in there. Now, you can see the wave moving up and down. But the energy, the wave itself, is moving forward. So they're perpendicular to each other. The wave moves up and down, and it's making the energy go forward. The wave itself is moving forward through the medium. The next type we have here is a longitudinal wave. And that wave is parallel to the direction of motion. So I'm going to do a little example up here with my slinky. Do it a couple of times. So you can see that the slinky is compressed, and that compression is like a wave pulse, and it moves through the slinky. So if I draw that out, it kind of looks like that. So this would be a wavelength, and this would be a wavelength. This means that it's being squished up, bunched up in the direction of the motion of the wave. So it's squished in this direction, and it's also moving in this direction. And when I do the slinky part, when I say wave pulse, that's just like a single one with that. And I could do a couple of them, 1, 2. And you can see them move back and forth in that slinky. And the last little one that we're going to talk about is surface waves. And there's some sort of transverse and also longitudinal. And I'll show you a picture in a second that kind of shows you why it's both of them. All right, so here's a picture of that slinky that I gave you, or that I showed you, except for when I did it at the end. What they did here is they pinched it at the middle, and then the wave goes out from either side. I would do that, except for I don't have great hands. So here's your surface wave. So it's some part transverse and some part longitudinal, and that's because your particles in your wave move both up and down and back and forth. They move in a circle, which is called an orbital. So it has some perpendicular movement and some parallel movement. So it's a surface wave because it contains both. So the energy moves along here, but the particles themselves kind of move forward and then they come back. So they're acting like rollers moving along the energy. So resonance is what happens when you add energy at regular intervals that match the period. The best way to imagine this is on a swing. You kick your feet out at the very top. Remember the pendulum, if we graph that motion over time, gives you a wave. So if you kick your feet out at the top, you can push yourself higher. And that's because you're adding energy, your physical, whatever you ate for breakfast energy, into it at the very peak of its wave. And that allows it to add energy to the wave, making it a larger amplitude, so you go up higher. Now, if you kick your legs at a different time, so when it's only 3/4 down, or if it's right down at the bottom part, you're going to slow yourself down because you're adding energy not at the peak of the wave. So you're actually taking energy out of the wave, slowing it down. So when the energy is added and the wave increases in amplitude, this is what resonance is. And we'll talk more about this when we get to the sound section in next week. I showed you this wave yesterday. We talked about the period and the amplitude. We're going to add a little bit to that. The period is the amount of time for one wave. If I write down period here, period is going to be it's in seconds, so it's seconds per cycle. So it's the amount of time for one wave. And when we talk about cycle, it could be wave, it could be pulse, it could be oscillation, it can be lap, orbit, just whatever it is that you're talking about that completes one motion. Wavelength. And we're going to add to this, and we're going to go frequency is the number of cycles per second. So sometimes your object is going so fast that it doesn't make sense to do the number of seconds per cycle, because then you're going to end up with it's only like 0.0001 seconds per cycle. That's not very helpful. So we flip it over and we look at it as frequency, where it's cycles per second. So it could be like 10 cycles in a second, or 100 cycles in a second. That's something that's vibrating really fast. So this one ends up just looking like seconds. That's its unit. And this one ends up being 1/seconds, which is equal to hertz. So your unit for frequency is hertz. And to convert from one to each of them, they are inverses of each other. So frequency is 1/period, and period is 1/frequency. And just like we were talking about yesterday, the amplitude is from the equilibrium to the highest point, or the equilibrium to the lowest point. It is not from the highest point to the lowest point. It is measured from the equilibrium. And the period is the amount of time it takes for one wave. So this would be your wavelength, and however long it took you from where you started to the end of this wave would be your period. Your wavelength, which is lambda, it looks like a wave with a little kickstand. It's going to be measured in meters for SI units, and it's the actual length of the wave. To calculate this, we use lambda equals velocity over frequency. Now, I don't like the way that that's set up. I like the equation, but it's kind of hard for me to remember. So I actually rearrange it so that it looks like this. That one is a lot easier for me to remember. So I usually write it like that. We can also turn it into period by converting frequency to period, and it will look like this, which is fairly easy for me to remember because velocity is in meters per second, and lambda is meters, and period is seconds. So you can kind of remember it that way. This one's a little trickier, meters per second, lambda's in meters, and frequency is in hertz, which is 1/seconds. To measure this wavelength, we're going to measure it either from crest to crest or from trough to trough, where the crest is the highest point of the wave and the trough is the lowest point of the wave. You can also measure from equilibrium point to every other equilibrium point. This has got to go through the whole up and down part of the wave, but that's hard for people to remember. So that's why we usually do from crest to crest or trough to trough. Okay, I have a practice for you here. And it says 7 pulses are generated every 0.5 seconds. And this is happening in a fish tank, so hopefully this isn't killing the fish. What is the velocity of the waves if the wavelength is 0.2 meters? So what is this 7 pulses? What does that mean? Say it again? Frequency? Okay, it's going to help us find the frequency, but by itself it is not the frequency. Anybody else have an idea? It's not wavelength. It says 7 pulses, so it's not really like a variable that we're usually used to finding. We just need to label it. Cycles, yeah, it's just the number of cycles, or number of waves, or number of pulses. It's not really one of our normal variables. And then what's this 0.5 seconds? Say it again? It's the time. It's not the period. It's not the period because the period's for 1 second or for 1 pulse. But this is for 7. So it's the time for 7 pulses or 7 cycles. So make sure you're careful about that. And I did this problem because there's one like this in your homework. And then we have the 0.2 meters. What's that? That's wavelength. What are we looking for? Velocity. All right, we're going to go over these velocity equations that I've made over here. Do you want to use the one with frequency or the one with period? It doesn't really matter which you use. Frequency? All right, that's fine. Velocity equals wavelength times frequency. So we need to find frequency. And frequency is cycles over seconds. So we have 7 cycles over 0.5 seconds for those cycles. We're going to end up with 0.14 hertz. We'll plug this into the equation. Velocity is going to be wavelength, 0.2 times 0. Why is it 0.4? I can't do math here. There we go, 14. That's better. 14. And we're going to end up with a velocity of 2.8 meters per second. So it's not that it's hard, it's just you have to make sure that when you're reading the problem, you're putting the correct variables to what it says. So anytime it says pulses or waves or laps or oscillations, all that means just the cycles, the number of waves. All right, I have, I think, 5 clicker questions for you today. Here's the first one. It says, if a wave performs 10 oscillations in 5 seconds, what is the frequency of the wave?